So in this video we will prove two theorems which are really very important from the point of view, as these results will be used when we will prove Unison's lemma or T's extension theorem. So what these two theorems are: the first one is theorem. First write down the statement and then we will move on to the proof. A topological space X top is regular if and only if for every point x belonging to x and for every neighborhood n of the point x there exists neighborhood m of the point x such that m bar is a subset of n. So this is the theorem, and now we will move on to the proof. Since here we are having if and only if, so we will have to prove it directly, as well as the converse part of the proof is also required. So first, let x top be regular. So we have taken a regular topological space, and now we have to prove for every x belonging to x and for every neighborhood n of x there will be a neighborhood m of x such that m bar is a subset of n. Let x be any arbitrary point of x and let n be an arbitrary neighborhood of the point x. Since n is a neighborhood of x, by definition of neighborhood, therefore there exists an open set G. Open set means a member of top, such that x belongs to G and G is a subset of n. Now x belongs to G, so that means x does not belong to G complement. G is open, that means G complement is closed. So there is a closed set and a point not belonging to that closed set. The space is regular. Therefore, there exist two open sets, say L and M, such that x belongs to M and G is covered by L. M intersection L is 5. So this condition will be there. Now x belongs to M. Earlier I have written x belonging to G is a subset of n. That will be required. Now M intersection L is 5. This implies here M is a subset of L complement. If M is a subset of L complement, then M bar is a subset of L complement bar. L is open, that means L complement is closed, and for a closed set its complement is same as it is. So you can write here L complement, so M bar is a subset of L complement. Here G is a subset of L complement, that means L complement is a subset of G, and G is a subset of N. G is a subset of N. Combine these three results. M bar is a subset of L complement is a subset of G, G is a subset of N. So you can say M bar is a subset of N. And what is M? M is open set containing X. Open set containing X means neighborhood of X. So that means there exists a neighborhood M of X such that this condition is satisfied, and that is what we need to prove. So this is first part of the theorem, and now we will move on to the converse part. For the converse part, we are given that the condition is satisfied. That means for every neighborhood n of x, there exists a neighborhood m of x such that m bar is a subset of, and that is given to us. And now we have to show that the space is regular. We have to show that the space is regular. So from where we have to start? We will have a closed set and a point not belonging to that closed set. So let F be a closed set and X be a point not belonging to F. X is not in F. So where X is? X is in the complement of F. So this means X belongs to F complement. Now X belongs to F complement and F complement is open because F is closed. So that means F complement is a neighborhood of X. And we know that if X is any point and there is a neighborhood of that point, then there will be another neighborhood M bar such that M bar is a subset of F complement. So therefore, by given hypothesis, there exists a neighborhood M of X such that M bar is a subset of F complement. Now M is a neighborhood of X. That means X belongs to M. This is clear. M bar is a subset of F complement. So if you take complement again, what you will get? You will get F is a subset of M bar complement. So you can replace this by F is a subset of M bar complement. M bar is a closed set, and complement of a closed set is open. So this is an open set. This is an open set. We have an open set containing X. We have an open set covering F. Now what else is required to be proved? That the intersection of these two is phi. Claim M intersection M bar complement is phi. Suppose, if possible, it is not phi. If it is not phi, there will be some point P in this intersection. So there will be some point P. So therefore, let P be a point in M intersection M bar complement. This means P belongs to M and P belongs to M bar complement. This means P belongs to M and P belongs to M bar complement. That means P does not belong to M bar. We know that M is a subset of M bar. We know that M is a subset of M bar. If P is not in M bar, how can P be in M? So that means P does not belong to M. No, P belongs to M and P does not belong to M. This is a big contradiction, and this is contradiction because we have supposed that M intersection M bar complement is not phi. That means it must be phi. So we have taken a closed set F and a point X not belonging to F, and we have obtained two open sets M and M bar complement, one containing X, another covering F, and their intersection is phi, which makes the space regular. So this was the first theorem that we proved today, and now I'll move on to the next theorem. Next theorem, write down the statement first. A topological space X star is regular if and only if for every X belonging to U. What is U? U is here an open set. U is here an open set. For every X belonging to U, there exists an open set V such that X belongs to V, V is a subset of V bar, and V bar is a subset of U. So this is the theorem, and once again, since there is if and only if, we'll have to prove it directly as well as the converse part of the theorem need to be proved. So I'll start the proof now. Let X tau be a regular space. Let X tau be a regular space, and let X belongs to U, where U is open set. Where U is open set. So X belongs to U means X does not belong to U complement. And since U is open set, U complement must be closed. So there is a closed set and a point X not belonging to that closed set. Space is regular, therefore there must be two open sets, one containing this, other covering this. So therefore there exist open sets V and W such that X belongs to V. On the other side, your U complement is covered by W, and V intersection with W is phi. X belonging to V, we need it. V is a subset of V bar. It is always true, without any doubt. X belongs to V, V is a subset of V bar. The only thing that is required to prove that is V bar is a subset of U. For that, we will use these two. So how to use these two to prove that V bar is a subset of U? First of all, look here. V intersection W is phi. That means V is a subset of W complement. Take closure on both sides. So V bar is a subset of W complement bar. W is an open set, so W complement is closed. Closure of a closed set is the set itself, so you can remove it from here. W complement bar is same as W complement, so V bar is a subset of W complement. From here, U complement is a subset of W, so W complement is a subset of U. V complement is a subset of W complement, and W complement is a subset of U. Combining these two, you can say V bar is a subset of U. So what you have proved? You have proved that there is an open set V such that X belongs to V. V subset of V bar is always true, and V bar is a subset of U. So what was required to be proved is proved. So first part, the straight part of the theorem is proved. Now we will move on to the converse. Conversely, let the given condition holds. The given condition holds. Given condition holds mean if there is an open set U and X belonging to U, then there always exists an open set V such that X belongs to V. V is a subset of V bar, and V bar is a subset of U. This condition is satisfied. This is given. And we have to prove that the space is regular. If we want to prove that the space is regular, from where we are to start, we'll take one closed set and a point not belonging to that closed set. So let F be a closed set and X be a point not belonging to F. X is not in F, so where X is? So X is therefore in F complement. F is closed, so F complement is open. This is an open set containing X, so there is an open set containing X. If an open set contains X, then there exists an open set V satisfying this condition. Here again, this open set contains X, so therefore there exists open set V. There exists open set V such that X belongs to V, V is a subset of V bar, and V bar is a subset of F complement. This is X belonging to V, it's okay. I have written it here. Now move on to the second condition. V bar is a subset of F complement. This means F is a subset of V bar complement. So this I require. This also I require because V is an open set, V bar is closed, V bar closed, its complement is again open. So F is contained in an open set, X is contained in an open set. Now what remains to prove is that intersection of these two is phi. So I am going to claim that intersection of V and V bar complement is phi, and the proof is almost done in the previous theorem. So claim is that V intersection with V bar complement is phi. If possible, let P be an element in V intersection V bar complement. This means P belongs to V and P belongs to V bar complement. P belongs to V bar complement means P does not belong to V bar, and V is a subset of V bar always. If P is not in V bar, how it can be in a subset of V bar? So it means P does not belong to V. P is in V, P is not in V is a big contradiction. And this is a contradiction because our supposition was wrong, and what our supposition was? Our supposition was that this intersection is not phi. So that means this intersection must be phi. So what we have proved? We have taken a closed set F, a point X not belonging to that particular closed set F, and we have obtained two open sets V and V bar complement, one containing X, another containing F, and their intersection is phi. That means our topological space is regular. So here I am going to stop this video, and both these theorems, both these results are very, very important, as we are going to use these two results in proving not only Urysohn's lemma but also in T's extension theorem. So wait for the next video where we will prove these two important theorems, Urysohn's lemma and T's extension theorem. Till then, thank you once again.